The chain rule is probably one of the most useful techniques in the process of differentiation, because really at the moment we only know from first principles how to differentiate certain simple functions. The chain rule will enable us to differentiate composite functions. Here are two functions we can differentiate. And our rule for differentiation is this: if y is equal to ax to the n, and to differentiate this, we bring the n down and multiply it by the a, and then reduce the power of x by 1. So we get dy dx is equal to an x to the n minus 1. And we do that for all terms. So the differential of the function in our example becomes dy dx is equal to, the 3 comes down and multiplies by the 5, so we get 15x, and we reduce the power of 3 to the power of 2, and that's the first term. Now this term, effectively there's a missing 1 here. So the 1 comes down, and the power reduces, x to the 1 becomes x to the 0, which itself is 1. So the second term differentiates to just minus 1. And the constant here, the plus 1, differentiates to 0. And for my second example, dy dx, by the definition of this function, the derivative is the same as the function itself. We just get e to the x. You may not have come across that yet. When you look at logs and exponentials, that will be explained. But take that as read for now. So as I said, this is really the extent of our knowledge as far as differentiation goes from first principles. So what happens if I turn our simple function into a composite function like this? Well, that's the same so far, but what about if I cube it? What would dy dx be? Yes, we could multiply this out. 3 brackets of 5x cubed minus x plus 1 all multiplied together. Yes, it's a possible way of doing it, but it's a lot of work. This is where the chain rule comes in. And the chain rule uses a substitution. You can think of the 5x cubed minus x plus 1 as a sort of inner function, which is then cubed. So if we give this inner function a name by substituting u for it, for example, we'll get y is equal to u cubed. So let's write that down. Let u be the inner function. Now we've not got y here anymore, but we can differentiate u with respect to x. So therefore du dx is equal to, well, it's the result we got up here, which is 15x squared minus 1. And what of the substitution itself? What does our function look like now? Well, y is equal to u cubed. Well, I can differentiate that by replacing u for x and do an ordinary differential. And I get dy du is equal to, the 3 comes down, power reduces by 1, 3u squared. But we need dy dx. Well, that's where the chain rule comes in. Let's have a look at it briefly. I hate doing this in any course, but in a way you're going to have to take this as read. You can treat dy dx as the multiplication of dy du multiplied by du dx. And effectively, can you see the du's almost act like a fraction and cancel out? Now, it's not a fraction in variables d, y, x, and u, but it's a concept that we can find the differential of a function y with respect to x by substituting u and then differentiating the function with our substitution in it, and then differentiating the substitution itself. So we've actually got the constituent parts of what we need. dy du is here. Yes, it's in terms of u, but we can easily substitute that back to x by just pushing our inner function back into our answer for dy du. And we've got du dx here. So we can write down the answer. So this is equal to, dy dx is equal to 3u squared multiplied by, du dx is here, and I'll put it in a bracket, 15x squared minus 1. So putting back our substitution for u, we get 3, there's our u, which is 5x cubed minus x plus 1, this time raised to the power 2, multiplied by 15x squared minus 1. And that is your answer. And that, I'm sure you agree, is a lot simpler than multiplying this guy out and then differentiating the terms separately. But what about our second example here? Well, let's make this more difficult. So we've got e now raised to the power 2x squared minus 3x plus 1. Yes, looks considerably more complicated. But again, we can do this by the chain rule. Effectively, this is our inner function. So I can say straight away, let u equal 2x squared minus 3x plus 1. du dx, by the first principles method that we've worked out, 2 comes down. We get 4x minus 3. Now we need to work out what dy du is. Well, y, because we've made the substitution, y is equal to e to the u. And therefore, dy du is equal to e to the u. That's employing exactly the same rule here. And all I've done is write a u instead of an x. So now let's use the chain rule. dy dx is equal to dy du multiplied by du dx. So therefore, in our case, dy dx is equal to dy du. dy du is e to the u. Well, I might as well take this opportunity to substitute back, u being our inner function, which so far is exactly the same as the function we started with. And we've got to multiply this by du dx, which is this, which is 4x minus 3. And that's the answer. Yes, I could do some tidying up and put the 4x minus 3 at the front of the e expression, but take a moment to appreciate what the chain rule has done for us. We're now able to differentiate composite functions. So in the tiny space I've got left, let me write what we've done in terms of function notation. So I'm just rewriting the chain rule in terms of f and g. So a composite function can be written down in fg notation as this. It's the f of g of x. And g of x here is our inner function. U is equal to g of x. So writing the differential down in function notation, we get dy dx is equal to f prime g of x multiplied by the differential of our substitution, which we can describe as g prime x. Now, I'm not certain writing the chain rule in that form is as memorable as our notation here, but I've shown it to you just in case in a book or another tutorial you see this expression written down and not realize that it's really the chain rule in disguise. Hope that's okay.